of mathematics can be made more fun, more relevant to students in the 21st century, particularly for emerging fields such as data science and machine learning, artificial intelligence, and more. Of course, for this particular audience, this distinguished audience gathered here today, one doesn't really need, let's see if I can advance this. There we go. One doesn't really need to say how critical mathematics and science education is for the next generation and for the next set of challenges that we will be facing in India and around the world. So I think all of us here agree that science and mathematics, in conjunction with tools from social science and other areas, will indeed be key for solving the prevalent issues of our time and achieving the 2047 vision for India. And these critical issues, of course, include climate change. They include pollution. We're having an air pollution problem here in Delhi right now. This is something that we really need to address. Climate change is part of the issues surrounding pollution as well. Waste management. Another new issue that's going to be confronting us very soon is the disruption to the employment landscape caused by AI, and much, much more. All these problems are coming at us, not just in India, but around the world, and it will be science and mathematics education in conjunction with other fields in social science and beyond that will allow us to address these problems, allow the next generation to address these problems. So mathematics and science education is truly critical. If the size can be made 4 by 3 again. Otherwise, some of the squares will become rectangles. Coming up. So becoming a, can the slide please be changed back? So becoming a leader in AI, in particular, will require the highest quality of science, mathematics, as well as multidisciplinary education across fields. That will be very, very important in becoming a leader in AI and addressing the various problems that are facing our society at this time. So the National Education Policy 2020 provided a blueprint to transform education, particularly in science and mathematics, but across the board, to prepare the next generation for the 21st century and India's vision for 2047. I'm trying to advance the slides. Oh, there we go. Yeah, tiki, okay. Okay, so the importance of multidisciplinary scientists and innovators. We want to make sure that it's not just science and mathematics education that's enhanced, but it has to be, education has to be enhanced across the board, across subjects. Steve Jobs is a great example. Steve Jobs was famous for his ideas for products that married top-notch aesthetics with top-notch engineering. And when he was asked about why the Macintosh computer revolutionized computing, he said, "I think part of what made the Macintosh great was that the people working on it were musicians and poets and artists and zoologists and historians who also happened to be the best computer scientists in the world." So this is a very important argument for having really broad background people working on our biggest problems. A survey of Nobel Prize-winning scientists showed that they are 3 times more likely than the average scientist to have an artistic hobby. We have some Nobel Prize winners with us today. We can ask them if they find this to be true amongst themselves. But this is also the case. Having that artistic sense an aesthetic sense is very important to make novel, creative innovations. So studying art, music, literature, language, philosophy, social science, and so on helps set a context for the science that's being studied, and vice versa. Moreover, studying art and music teaches creativity, which is essential for innovation. So the argument is that together with top-notch science and math education has to be accompanied with a strengthening of social science and art. And progress in AI will definitely require multidisciplinary knowledge across mathematics and science, as well as social science, because we have to know what the needs are for humanity and for the planet, for culture, for ethics, for law, before one can use the science and mathematics to make progress on social problems. So based on these foundational concepts, the NEP recommended very strong education in science and mathematics together with social science and humanities. And the NEP on mathematics education in particular said that mathematics and mathematical thinking will be very important for India's future and its future leadership role in the numerous upcoming fields. I think there is a slide. So based on these foundational concepts, the NEP 2020 recommended the following initiatives to make sure that science and mathematics education is strengthened. First of all, it's well established by neuroscience research of the last few years that about 90% of children's brains are completely developed by the time they're 6 or 7 years old. And so developing that evidence-based thinking as a child is important for them to have that evidence-based way of thinking for the rest of their lives. And so providing outstanding play and activity-based early child education to all is key to put everybody on a level playing field, make them school ready, especially first-generation learners. We must make free education in the early years available to all children, even before the age of 6, for 3 to 6-year-olds. And that's something the government is already working on, and that will be transformative for math and science progress in the next generation. The other important thing for math and science education is that it should be holistic, as I said, multidisciplinary, flexible, and discovery and play-based, engaging and enjoyable, less rote-based. So this is, if you develop that feeling of play when one is doing science, then one is more likely to make those crucial innovations. As Professor Gaim related in his Friday night research activities, play-based thinking about science and mathematics is the most productive. The NEP also recommended bilingual education in science. That's something that's now being developed in the new textbooks, so that students can grasp and think deeply about science in their own language. And the next 2 points are that there will now not be any hard separation of streams. Starting next year, there will not be any such thing as science students and art students and commerce students. It used to be that every student after 10th grade had to choose whether they're science or arts or commerce. That will end next year. Students will just be students starting next year, and that's huge, and that means students can take Tamil literature while also taking physics, they can take music while also learning chemistry, and so on. And so this is that multidisciplinary kind of thinking that will finally start in the formerly rigid system that we had in India. Our aim will be to develop scientific temper in every subject at every level. Even when one studies social science, it should be evidence-based. It should be based on experiment and logical thinking and conclusions. And so that is another important aspect in transforming maths and science and scientific temper in every student. And then one very important thing that will happen starting next year is that there will be a specialized multidisciplinary course, elective, in AI and AI-related content for grades 11 and 12 for those who want to learn it, so that we prepare a number of young people in this emerging field in a multidisciplinary and holistic way. So that's a summary of the new recommendations for maths and science education and the transformations that are coming over the next few years. And it's very exciting, and we really hope that that will create a revolution in science and science innovation in India as the next generation graduates from school. Okay. So for mathematics education, I want to get a little bit more into mathematics education, and there, in order to train our students in AI, pattern recognition plays a central and foundational role in mathematics and in AI and in machine learning, data science, because it's pattern recognition that enables machines to interpret complex data, such as images and speech and text, by identifying structures and regularities, thereby giving more meaningful output, more meaningful predictions. That's broadly how AI works. And so that is why the National Education Policy had recommended that every student should learn pattern recognition and computational thinking. So teaching the science and art of patterns, which is what mathematicians view mathematics to be, as well as computational thinking, algorithmic thinking, is so critical to ensure future readiness for AI and related fields, data science, machine learning, and so on. And so what I want to move into next is a way of teaching pattern recognition, the science and art of patterns, that makes it more fun and really teaches the core skills through play. And so I'll give some examples of how the science and art of patterns can be taught, and I hope that you will also enjoy that process. It's a very personal one for me, because this is how I myself got interested in mathematics, and the hope is that many more young people may get interested in mathematics through similar stories and through similar activities. So the science and art of patterns, that's what we mathematicians view what mathematics is. So mathematics may be viewed as the art and science of understanding patterns. And it's not just about finding the patterns, but it's about finding good explanations as to why those patterns exist. Because we're not just interested in knowing that the patterns are there, but we're interested in knowing why they're there. What is behind those patterns? What causes those patterns to exist? Because if one understands why they exist, then such explanations can often then be used in applications well beyond the context in which they were first discovered. And that can then help propel humanity forward. And there have been many examples of that throughout history. For example, when patterns from time immemorial were observed in the motion of planets, that led to the theory of gravitation, eventually allowing us to now launch our own satellites and so on. Or when patterns in genomes were discovered, those patterns are now helping in curing disease. As I mentioned, machine learning and AI are all about observing patterns, understanding why they're true, and then applying them in different contexts to make high probability predictions. So pattern finding and understanding why patterns are true lies at the heart of mathematics, but really lies at the heart of much of science and what has propelled humanity forward. And so getting young people to really understand patterns and why they exist, and from a young age, is something that is critical for the next generation to really make innovations. And so a lot of pattern recognition and pattern activities have been put in the new round of textbooks for science and mathematics and beyond that will be coming out over the coming couple of years. So one of the most fundamental places to see patterns are just around us, in numbers and in nature. We learn to count, we start seeing patterns when we look around us in nature, and even inside our buildings, we see patterns everywhere. And for number theorists, number theory is the area that I work in personally, our natural world is the universe of whole numbers, or integers. So minus 3, minus 4, minus 5, and so on, all the way to minus infinity, and then you have 0, 1, 2, 3, 4, the counting numbers. These numbers are our universe for number theorists. So we study the integers, and integers form the most basic objects in which to look for patterns. And number theory is the branch of mathematics that studies patterns of whole numbers, of integers. And number sequences are perhaps the most basic types of patterns that mathematicians study. So sequences of numbers are the most basic types of patterns, and so that's a very natural place to start in understanding patterns around us. So here are some examples of number sequences that you all would have seen before. So this is the easiest number sequence that exists. It's 1, 1, 1, 1, 1 forever. This is called the all ones sequence. Okay, so that's the easiest sequence. Then we have the next most complicated sequence is just the counting numbers, 1, 2, 3, 4, 5, 6, and so on. These are the counting numbers. And then gradually their complexity of sequences increases, that one studies. 1, 3, 5, 7, 9, these are the odd numbers. We have the complement of the sequence, 2, 4, 6, 8, 10, which are the even numbers, that's right. And then we have this sequence, 1, 4, 9, 16, 25, 36, 49, and so on. What are these? The squares, that's right, these are the square numbers. So this is given by 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on. What about this sequence? 1, 8, 27, 64, 125? The cubes, that's right. So it's 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, and so on. So these are the cubes. And then here's another level of complexity, 1, 2, 4, 8, 16, 32. What are these called? Right, these are the powers of 2. So here the sequence is made by at each point you double the previous number. So the next one would be 128 times 2, which is 256. So as you can see, in each of these sequences, the order of growth is getting bigger. The first one was constant, the next couple were linear, the ones after that were polynomially increasing, this last one is exponentially increasing because at each step you're actually increasing by a factor, not just by a fixed common difference. What are these? 1, 4, 16. Right. Each time we're multiplying by 4. That's right. So these are the powers of 4. And so on. So these are all examples of number sequences. Of course, they get more and more complicated in terms of order of growth. But at the same time, there's a lot of structure in these sequences. And a lot of these sequences are related to each other in surprising ways. So there are relations among sequences. So sometimes the sequences can be related to each other in surprising ways. So here's one of my favorite examples that always excites students when they first see this. What happens when we start adding up odd numbers? So we just take the number 1. Okay, well if you add up just 1, you get 1. But what if you take the first 2 odd numbers? Okay, 1 plus 3. What do you get when you add 1 plus 3? Okay, you get 4. Okay, what if we add the first 3 odd numbers? In other words, if we take 1 plus 3 plus 5, what do we get then? We get 9. 1 plus 3 plus 5 plus 7? Well, we just have to add 7 to the previous one, so that's 16. What happens if we do 1 plus 3 plus 5 plus 7 plus 9? We get 25. Everyone see the pattern there? We're getting 1, 4, 9, 16, 25. So if we take 1 plus 3 plus 5 plus all the way up to the nth odd number, which is 2n minus 1, we'll get n squared. That's right. That's what the pattern seems to say. So somehow the odd numbers are related to the square numbers. That's a surprising relation between 2 of the sequences that we had on the previous page. And so that's a beautiful pattern. Odd numbers are related to square numbers. But now the question is, well, why does that happen? Why does it happen that when you add up odd numbers, you start getting the square numbers? So remember, it's not just about finding the patterns. It's about understanding why those patterns exist. So why is it happening that when you add up odd numbers, you're getting square numbers? And when you first give this problem to students, and you don't tell them the answer that you have in mind, they come up with various different ways of understanding this. And so there are many different ways of understanding why this is true. Some can use algebra, some will use more geometric arguments, some will use induction. My favorite way of understanding why this is true is a picture. And it's actually very important. We often in the classroom teach things very mechanically, and so we would just come up with a mechanical algebraic way of proving that. But a picture, as they say, is worth 1,000 words. If you just give one picture, you can actually understand why this is true. And if you show it pictorially, visually, a student never forgets it. So if you haven't seen this picture before, when you see it today, you will never forget it, and you'll always know why adding up odd numbers gives you square numbers. It's this picture. So what is a square number? It's just the number of dots in a square grid, right? So for example, here we have 6 dots on one side, horizontally, 6 dots vertically, and so the total number of dots here is 6 times 6, which is the square number 36. And why is 36 the sum of the first 6 odd numbers? Well, the way you can see that is by drawing these red L's. And within each of these L's, if you look at the bottom left corner, there's just 1 dot there. And then if you look in the next layer, you'll see that you have 3 dots. And then if you look in the next layer, you see you have 5 dots. And in the next layer, you have 7 dots. And then 9 dots. And then 11 dots. So therefore, 1 plus 3 plus 5 plus 7 plus 9 plus 11 is 36. And that's why the sum of odd numbers in a row gives you the square numbers. Isn't that pretty? And this is something that you never forget once you've seen it. Clearly this argument, right, would work for any square number. You write down any square number, you write it as a square grid of dots, and then you make these L's, and you'll see that each time you make an L, you make up the next odd number, and so therefore the sum of those first n odd numbers will give you the nth square number. And so that implies that the sum of the first n odd numbers is the nth square number. This way of visualizing is very helpful in understanding why things are true. In mathematics, this is often called a proof without words, because you don't need any words, you just need a picture, and you understand why it's true. Here's another example of such a relation between sequences. Suppose you start taking the counting numbers and you add them up, and then you add back down. Okay. So what do I mean by that? Okay, 1 is equal to 1, but if you go 1 plus 2 plus 1 and add them up, what do you get? That's right, 4. What if you go 1 plus 2 plus 3 plus 2 plus 1? What will that be equal to? 1 plus 2 plus 3 plus 2 plus 1. That's right, it's 9. 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. That's right, 16. Look at that, we're getting the same numbers again. And what that seems to indicate is that if you take all the numbers up to n, 1 plus 2 plus 3 all the way up to n and then down to 1, what do you expect to get? The nth square number, that's right. So there's another way of making square numbers is by adding numbers up and then back down. So that's the pattern, but remember we're not just about finding patterns, but we want to understand why they're true. And can you find a similar pictorial explanation for this? So it turns out there's another pictorial explanation that would explain this. If you're bored for the rest of the talk, you can think about this. Or maybe you already see it. Okay. So a lot of these kinds of observations can be explained using pictures, and once you make the picture once, you remember it forever. And so that's why this is a good way of teaching students, because they never forget it then. Whereas if you teach them a proof by rote using algebra, they forget after their next exam. Okay. My favorite problem as a child was about stacking oranges. My family really enjoyed fresh orange juice, and my mother, who's here, used to bring lots of oranges to the house. Though to her dismay, before the oranges were used for juicing, I started making stacks of them in pyramid shapes. And so I would take these oranges. This is the way oranges are stacked in the supermarket as well. On the street, you'll see when oranges are being sold, they're packed in this way because this is the tightest packing of spheres, tightest packing of balls in 3-space. And so oranges are often stacked this way, and I enjoyed trying to reproduce these pyramids at home. And a question that immediately arose, if I was trying to make a pyramid with 4 oranges on each side, well, how many oranges would I need to complete that pyramid? If I wanted to make an orange stack with 10 oranges on each side, how many oranges would I need? And that was a problem. That was one of the problems that really attracted me to mathematics early on when I was a child. And problems like this, I find now when I use them in the classroom, it really excites students because it really shows the power of mathematics. Because once you have that formula for how many oranges you need, and then you start making the pyramid, and you collect exactly the right number of oranges using the formula, and then you get to that last orange, and it just comes perfectly on top. Because you knew the formula in advance. That's a very enlightening moment, and it really makes you feel the power of mathematics. So how many oranges are needed to make a pyramidal stack, having n oranges on each side? So if you think about it, if you just have one orange on each side, you just need one orange. But if you have two oranges on each side, you have to put 3 oranges on the bottom, right, in a triangle, and then you put that one on top. So you need 4. And it turns out if you have 3 oranges on each side, to make the stack, you need 10, and then 20, and then 35, and then 56, and so on. And what is the formula for the nth term? And this, for me personally, was the first math theorem I ever solved, and it really excited me about mathematics. The formula is n plus 1 times n plus 2 divided by 6. And that formula there, so in other words, if you want to know how many oranges you need with 5 oranges on each side to make a stack with 5 oranges on each side, you just have to do 5 times 6 times 7 divided by 6, which is 5 times 7, which is 35. And there it is. And so this is an exercise that really shows the power of mathematics, because you can now just start with 35 oranges using this formula, and you put 5 oranges on each side, you start making the pyramid, and when you get to the 35th orange, it just fits perfectly on top. And that's always an exciting moment for the child, where you could predict in advance that you just need that 35th orange to come on top. So nature is actually a great source of number sequences and patterns. The most common number sequence in nature is this one. 1, 2, 3, 5, 8, 13, 21, 34, and so on. How many people have seen this sequence before? It's very common. So these are called the Virahanka-Fibonacci numbers, as I'll explain in a moment. So Virahanka is a linguist who lived in the 7th century. And Virahanka wrote this beautiful, so he wrote in verse, and a translation of his verse is that write down the numbers 1 and 2. This is in the 7th century. Write down the numbers 1 and 2, and then each subsequent number you write down is the sum of the previous 2 numbers. Now why was he writing such a verse to make such a sequence? He was a linguist. This is back in the 7th century. So I first learned about these numbers from my linguist grandfather as the Hemachandra numbers, named after the linguist Hemachandra, who lived in the 12th century. But these numbers were also written about by Gopala in the 12th century. So a number of linguists were writing about these numbers all the way back in the 7th century, and some even earlier, and some later. But linguists were the first people interested in these numbers. Of course, now in India, they're known as the Fibonacci numbers, after Fibonacci, the Italian mathematician who was born 500 years after Virahanka. But in many parts of the world, the name has been, as a transitional name, Virahanka-Fibonacci numbers are being used. And but what this shows is that Fibonacci was not the first person to discover these numbers. In fact, he was not the second or the third. So that's why the name is being referred to often now as the Virahanka-Fibonacci numbers, now that we know more about the history of these numbers. And I want to explain why these numbers come up in linguistics in a natural way, and in poetry, and in music. And I love this story because it shows how something so fundamental in mathematics, the Virahanka-Fibonacci numbers now have an entire journal dedicated to them, where it's only about, the journals are published only about those numbers. It's called the Fibonacci Quarterly. So these numbers are so important in mathematics and science, and yet they were discovered in the context of poetry and music. And I think that's a beautiful story and really shows the power of interdisciplinary thinking. So why were Sanskrit and Prakrit, and now these numbers are also used in Telugu poetry, Malayali poetry, Marathi poetry. Why were Indian linguists interested in these numbers? Well, it turns out poetry in many languages, Telugu, Malayalam, Sanskrit, Prakrit, Marathi, all have this structure where the poetry consists of syllables, each of which is either long or short. And what's more is that a long syllable, when you pronounce it, lasts 2 beats, and a short syllable lasts 1 beat. And so ancient poets were interested in this question. Well, suppose I have 8 beats of poetry left in my stanza. How many ways can I fill it in with long and short syllables, where a long takes 2 beats and a short takes 1 beat? How many ways can one do that? So for example, if you want to make 8 beats, right, and the long is 2 beats and a short is 1 beat, you could do long, 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 right? That would be 8 beats. But you could also do short, 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 right? That would also be 8 beats. Or you could do various things in between. Short, long, long, short, long. Long, long, short, short, long. So the question is, how many total ways can one fill in 8 beats with long and short syllables, where long is 2 beats and a short is 1 beat? And it turns out it's the Virahanka-Fibonacci sequence that gives the right answer. So you write down the sequence that Virahanka wrote, you write down the numbers 1 and 2, and then each subsequent number you write down is the sum of the previous 2. And now if you want to know how many rhythms of long and short syllables have 8 beats, you just take the 8th number of the sequence, which in this case is 34, and therefore there are 34 rhythms having 8 beats consisting of long and short syllables. And this was the theorem that described by Virahanka way back in the 7th century in a book about linguistics and poetry. The poetry community and the music community in India was often separate from the modern mathematics community, and so this was sort of unknown in the mathematics and science community until recent years. But this is a very natural way of coming up with the sequence, as opposed to the one given by Fibonacci, which involves this unnatural story about how rabbits multiply. But this was actually used in applications in music. If you're a mridangam player or a tabla player, you actually have to use the sequence to enumerate all rhythms that can be played in a certain number of beats when you improvise. And so this was actually a practical application that arose more than 1,000 years ago that's still used today in the artistic traditions of India. The reason that there's entire journals dedicated to these numbers now is that these numbers, the Virahanka-Fibonacci numbers, actually arise all throughout nature. So for example, the number of petals on a daisy tends to be one of these numbers. If you look at this daisy here, you'll see that it has 13 petals. If you look at this daisy here, you'll see that it has 34 petals, 34 being the same as the number of rhythms having 8 beats. And this is one of my favorite pictures here. It's an entire garden of daisies. Each one of these daisies has 55 petals. And I know that because I actually sat and counted it. Yeah, so these actually all have 55 petals. So the number of petals, and there's some breeds of daisies that have 89 petals. So it's quite amazing. The daisies are just fantastically good at creating the Virahanka numbers. So in a sense, nature discovered Virahanka numbers even well before humans did. And there's a good reason that we now understand on why this happens. Why do daisies have a Virahanka number of petals? It has to do with the fact that the petals sprout from seeds that are in the center of the flower, and the tightest packing of seeds in a spiral arrangement has to do with the golden angle, the golden ratio, and so when you have a full round of that spiral, you actually add up to the next Virahanka number. So there's a natural explanation in terms of evolution for why these are the right number of petals, the optimal number of petals to grow if you want your tightest packing of seeds in the center. These numbers also come up on pine cones. If you count the number of spirals on a pine cone, it tends to be one of the Virahanka numbers. In fact, you can count spirals in both directions, and they tend to be consecutive Virahanka numbers. So for example, here you see that this pine cone has 13 spirals going counterclockwise. It has 8 spirals going clockwise, which are consecutive Virahanka numbers. So this is the most popular sequence, number sequence in nature, and also the most popular number sequence among artists, which now has so many scientific applications, but it was first discovered in an artistic context, and that is a very inspirational story about cross-disciplinary thinking, art leading to a discovery in science. What's the most beloved sequence for number theorists? The most beloved sequence for number theorists are, of course, these numbers here, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on. What are these numbers? The prime numbers, that's right. The prime numbers are the most beloved and important sequence for number theorists. A prime number is a number that has exactly 2 numbers that exactly divide it, 1 and itself. 3 minutes? Okay. So prime numbers are the atoms of our universe of whole numbers. Every positive whole number can be expressed in a unique way by multiplying together prime numbers. So for example, 384 can be written as 2 times 2 times 7 times 13. That's a unique way. That's its breaking up into atoms. And every number can be broken up into atoms in a unique way. It used to be thought that prime numbers are just there for the fun of number theorists, and they have no applications. But in fact, they're now one of the most important numbers in science and mathematics. And we now know that prime numbers were also discovered by nature before humans. Cicadas are these bugs that live underground, and they come out every 13 years, or every 17 years, or every 19 years. So cicadas kind of discovered prime numbers before humans, in a sense. So they tend to come out every prime number of years. And why is that? That was only understood fairly recently as well. It has to do with the fact that cicadas want to avoid predator cycles. And to best avoid predator cycles, it's best to come out in long prime number of year cycles. And that makes you the least likely to go extinct. If you come out every 2 years and your predators are coming out every 6 years, then you're going to just be hit every single time you come out. And in modern times, prime numbers play a very important role in our lives due to the following fact. Prime numbers are just super important. They come up in our lives every single day. And the reason is that suppose you have 2 200-digit prime numbers, okay? And you multiply them on your calculator or on your computer. A computer will calculate the product of 2 200-digit prime numbers in a fraction of a second, just like that. And it'll give you a 400-digit answer. But if you take that 400-digit answer that you got by multiplying 2 big prime numbers, and you put it in another computer, in fact, you put it on every single other computer in the world, and you ask it to find those original 2 200-digit prime numbers. So if you start with a product of 2 numbers and try to find the 2 things that you took the product of, try to do that reverse process. The best known algorithms working on all the world's computers with the best AI models that we have available would take billions of years to find those 2 prime numbers. And that's crazy, because it takes only a fraction of a second to multiply, but it takes billions of years to go the reverse direction, even with all the intelligence in the world, all the computers in the world. And this is what all our modern communication is based on. When we talk on the cell phone, our voice is encrypted using this fact that we can multiply prime numbers quickly, but we don't know how to go the other way. Only if you know that original prime number are you able to decode your conversation on the cell phone. And so this is how your credit card security, phone security works, is using these prime numbers. So the fact that it's easy to multiply but hard to do the reverse process is the basis of much of the world's encryption. And often when we submit private information on the internet, prime numbers are what are being used to encrypt the information and protect it. And since no one knows how to factor numbers, in other words, do the reverse process, or so we think, this method of encryption is presumably secure. And one of the fundamental problems in number theory is either to prove that it's difficult to go backwards and factor, or to find a quick way to factor thereby making all these encryption systems like RSA useless. This is one of the fundamental problems in number theory. So maybe I'm going to end just by talking about my favorite number, which is a pattern that excited me as a child, and I find that it excites many other people. One of my favorite numbers, when we used to talk about our favorite numbers as children, a lot of people would say 6 or 7 or 11, and then they would ask me, and I would say 1,42,857. And everyone would ask, why? And the reason, it's a very special number. If you haven't seen this before, it's quite amazing. The amazing property of 1,42,857 is that, well, if you multiply it by 1, you get the same number back. Okay, well, that's not that exciting. but what happens if you multiply it by 2? I claim you still get the same number back. If you multiply it by 2, look, you get 1,42857, just with the numbers cycled around. What happens if you multiply it by 3? You get the same number again, 1,42857, just with the numbers cycled around. What if you multiply it by 4? Again, you get the same number, but with the numbers cycled around. Or if you multiply it by 5, you get the same number back, 1,42857, but with the numbers cycled around. And even if you multiply it by 6, you get the same number back, 1,42857, but with the numbers cycled around. Isn't that amazing? So when you multiply 1,42857 by the first 6 numbers, you get the 6 possible ways of cycling around the number back. And there's a question in number theory that asks, are there other such n-digit numbers? So that if you multiply by 1 through n, you just get the same number back with the digits cycled around. Are there other such numbers? 1,42857 is the smallest one. And the question is, are there bigger ones, n-digit numbers, such that if you multiply by all the numbers from 1 through n, you get the same numbers back, but with the digits cycled around? And it turns out there are other such numbers. And the next biggest one is this 17-digit monstrosity. And you can take a picture of this and try it on your calculator. If you multiply this number by any number between 1 and 16, this is a 16-digit number. If you multiply by any number between 1 and 16, you'll get the same number back, but with the digits cycled around. And the question is, how do you find such numbers? What is the theory of such numbers? And more importantly, are there infinitely many such numbers? That's a question whose answer is unknown. We don't know whether there are infinitely many such numbers. And this pattern that I got to learn about as a child is now something that I think about in the context of much more sophisticated mathematics. It turns out that this problem is related to the Riemann hypothesis, which is one of the great problems of mathematics. But this pattern shows that you can really introduce children to some of the most sophisticated problems, the most important problems of mathematics, just by playing with simple patterns involving numbers. And so that's the message I wanted to give today. There are patterns all around us. Sometimes they seem trivial, they seem playful, but in fact they often connect to very, very deep things that can change the course of science and mathematics. And this is one example of them. So I'll stop here. Thank you very much for your attention. Thank you.
It was an extremely interesting talk, and I'm very sorry to cut you short because we were already overrun. So it's time for question and answers. Any, yeah.
Yeah, so it's an excellent talk. I have a quick questions to you, Professor. First thing, you being an architect of the national education policy, I would like to know what are the contrast and similarities of our education policies compared to the similar policy in other developed country. And second question, you have very nicely brought out that people excel in their area of specialization if they have other perspective like art or some other thing, which you said you should inquire from Nobel Laureate. So instead of that, you being a field prize winner, I would like to know what are the qualities God has gifted you, which you are permitted you to excel in your field. So please answer these two questions. Thank you.
Thank Thank you. The second one is more, I don't know how to answer that, but the first question is a very good one. When our committee was deliberating on what to put in the national education policy, we did indeed go through the education policies of many countries where education is at a very high level, including Finland, Singapore, the United States, France. So we did go through some of the education policies and we took the best practices from around the world. And one of the very best practices actually originates in India, in a sense. What are the best universities in the world that do the best research? You'll find that they're the ones that are multidisciplinary, that work across fields, that have faculty across fields of excellence, and they have students who take courses across fields. So one of the, perhaps the first university in the world that had that system was Nalanda. Nalanda was a multidisciplinary university, and it was a center of excellence where people from around India and around the world wanted to come to learn. And now, from Nalanda now to the modern day, what are the universities today that really exemplify the highest quality of learning and research? They're the Ivy Leagues, MIT, Oxford, Cambridge, Caltech, and all those universities. You can look at all of them. They have the property that they have outstanding departments, not just in science and mathematics, but also in humanities and arts and so on. Even MIT, which often is viewed as a technological institution, has outstanding arts departments, outstanding humanities departments, and every student who goes to MIT takes at least 8 courses that are not science, mathematics, or engineering. So yeah, this move back to multidisciplinary education, which India actually had, the example I showed, the Virahanka numbers really showed that it was linguists and poets that were doing mathematics, it was mathematicians who were doing arts and humanities. This was India's ancient tradition. We forgot it in India during colonial times, but it's something that should be brought back, because even today the best institutions of the world are like Nalanda, the multidisciplinary, holistic kind of education that make you all-round excellent in multiple subjects while being able to contribute at the highest level in specializations. So that, I hope that answered the first question. I was lucky to grow up in that kind of tradition. In my family I had experts across fields, and I got to experience that at home, and I think that's what really helped. A lot of my mathematics that I did, I was certainly inspired by artistic pursuits to make mathematical discoveries. So I feel like I was part of that, lucky to be part of that tradition, ancient Indian tradition.
Any other question? There, the back, yeah.
Dr. Bhargava here. So you explained through this picture that the sum of odd numbers is like squares, how to show it pictorially. So, but in that picture we can see some periodicity. So is there some mathematics about that periodicity also? Because without periodicity it will be difficult to understand through picture.
I don't know if it's periodicity, but it's a pattern.
Yeah.
Periodicity is an example of a pattern, and sometimes a pattern is periodicity, but sometimes patterns are something where it's not necessarily periodic, but it's growing at the same rate. So odd numbers are growing at the same rate, and that's the pattern there. But sometimes you see periodicity. I'll give you an example. In that when I was talking about my favorite number, 142857, if you have your calculator out, I can tell you how you can remember the number 142857. On your calculator, you just write 1 divided by 7 equals. And what do you get? Try it on your calculator. If you take 1 and divide it by 7, you get 142857, 142857, 142857 forever. 0.142857, So that's an example of periodicity, and that periodicity is actually behind what gives that number its special property. So you have a very good question. A lot of times the patterns that we see are related to periodicity, but sometimes it goes beyond periodicity.
Okay, thank you very much. Thank you.
Good afternoon, sir. Myself, Henika Arora. Being a mathematician, I just want to ask your views on the numerology. As in the universe, you said every creature follows some pattern. So do you think numerology is working for the human beings?
Well, yeah, if the numerology is based on evidence, then it definitely is. So Yeah, so the numerology, for example, that the cicadas discovered, they weren't just using prime numbers because prime numbers are cool and they're the atoms of our universe of big numbers, but there was also a good reason behind that numerology. Coming out every prime number of years, every 13 years. If you come out every 13 years and the predators that eat them come out every 6 years, it's only every 78 years that they would align. So even though it used to be considered numerology, oh, cicadas like to come out every prime number of years, eventually we understood that there's a reason behind why that numerology works. And again, it's all about not just the patterns, which is the numerology, but it's about why those patterns exist. And that's the evidence behind being able to use those for predictions.
Any question?
Question. Yeah. From this side. Right from you, straight. Right from you, straight. Okay. I am Pradeep, Professor of Biomedical Engineering, School of Biomedical Engineering. I am chemist and I work in interface between life science, materials and biology. Initially, for a few slides, you mentioned that there is a strong correlation between mathematics and AI. But as an interdisciplinary scientist, I feel that AI can fail somewhere. As a mathematician, where AI can fail and what is your opinion on that?
Yeah, AI fails quite a lot, especially in science. We've all, I think, tried to use AI to make it say something smart about science, and it often says total nonsense with complete confidence. And then you ask it again and it says it with even greater confidence. and the reason is that it's actually, what AI is still doing is finding patterns, but it is not understanding the explanations. And that is where we're failing with AI at the moment. We don't actually know, in most cases, why AI works. This is one of those few areas of science where the practice has gone much further than the theory. So we use AI because it seems to work, but we don't actually understand why it works and where it works and when it's going to fail. And this is a major obstacle to using AI for very important tasks, like scientific discoveries, or saving people's lives, or doing healthcare. It's one of the major obstacles. And so one of the major unsolved problems of AI is to understand why it works. AI should also start to incorporate explanations of patterns and not just use patterns, because if you just use patterns blindly and apply it elsewhere, it is going to lead to failures, and that's what's happening right now. So we will have to understand where it's possible for AI to fail, and where we can prove that it definitely works. And that is an open problem right now, because the practice is way ahead of the theory. We don't have a theory that explains or predicts when AI will get it right and when it will get it wrong. And so that's one of the major problems that AI has to solve. But it is, again, about that first slide that I said, we need to understand patterns and find the patterns, but we need to understand why those patterns hold. We need to understand the explanations behind them, and AI is not using those explanations at the current time. And that's why I fail so much.
So, Professor Bhargava, I'll have the privilege of asking you the last question.
Sure.
I just wanted to know, I'll turn back to the science and mathematics part that you were mentioning right in the beginning, what role it's going to play in the Viksit Bharat 2047. Now, Government of India has recently announced some schemes like the ANRF and also the One Nation, One Subscription. Do you think these schemes are actually going to make innovation, R&D and innovation very inclusive, and it will help us in following the theme what Government of India has actually envisaged for 2047?
Oh, absolutely. These two schemes that you mentioned are just fantastic, and I congratulate the government and the PSA's office and the Department of Science and Technology for taking these initiatives. ANRF is very, very important because it will allow research to start to happen across Indian universities, including state universities, where research used to be in a nascent stage. We have so many PhDs in the country, but 90% of them are at state universities where almost no research happens. Yes. What a waste of talent, right? We have so many PhDs, and 90% of them are not engaged in research and not able to engage in research because the funding is not there. So ANRF can really make a difference there in bringing research to the masses of PhDs that are in the country, so that research really becomes a possibility for everyone and not just those who are at the elite few universities. So that initiative can really change the research landscape of the country. And then One Nation, One Subscription, again, subscriptions are very, very expensive to journals, and state universities, very few of them had access to it before. Now that we have One Nation, One Subscription, and ANRF is there to fund research, and then One Nation, One Subscription is there for those researchers to be able to have access to journals. So those two initiatives together will make research a possibility for the 90% of scientists for whom it was not possible before. And so we should really take that as far as possible to create huge innovations in the country.
Thank you, thank you. Let's thank Professor Bhargava for a wonderful and engaging talk.
Thank you so much. Thank you.
May I now request Dr. Parvinder Maini to present a small memento as a token of our appreciation